Hello, everybody. Good morning. Let me begin by thanking the organizers for the opportunity to speak. It's a great honor and pleasure to be here. So the title of my talk is Stability of BPS States at Weak Coupling. And it's based on a paper I put out last year and some work in progress with my student, Safarazi. So the motivation for the talk is the distance conjecture, or weak gravity conjecture, in a Swampland program, which proposes that at infinite distance, or weak coupling limits in moduli space, an infinite tower of charge states should become exponentially light relative to the Planck mass as a function of the distance, or more precisely, the weak gravity conjecture would say that if you send g to 0 in the theory of quantum gravity, there should be a tower of states whose mass scale goes like g times m Planck. And usually sending g to 0, well, I think always sending g to 0 is infinite distance in moduli space, and then that mass scale is also exponentially light in the distance. So that's the motivation for the talk, but the results are more general, and they shed some light maybe on what's going on in this infinite distance and in this tower of states. So that's the talk. So we can study these conjectures, if you like, in a controlled setting in type 2b string theory, compactifications on Calabi-Yau threefolds, which yield a four-dimensional n equals 2 supergravity. And this n equals 2 supergravity has U1 gauge symmetries that come from the Riemann-1 sector, and the gauge coupling of these gauge symmetries are controlled by the complex structure moduli of the Calabi-Yau. So going to g goes to 0 limits is moving in the complex structure moduli space of the Calabi-Yau. And the states that are charged under these U1 symmetries, so these are the states that should form this tower of states that become light, are D3 branes wrapping 3 cycles in the Calabi-Yau. And we'll consider in particular the states which are supersymmetric, so BPS states. Geometrically, it means that the D3 branes wrap special Lagrangian submanifolds. So that's the setting in which we want to understand weak coupling limits, g goes to 0 limits, how these wrapped D3 branes become light, and how do they behave. And this, I think, studying this complex structure moduli space of Calabi-Yau is perhaps the most complete setting in which we can study these conjectures, because this moduli space has a very special property, g to n equals to supersymmetry. It doesn't receive alpha prime or g-string corrections, which means that it's an example of a moduli space in quantum gravity where we understand the full space. So there's nowhere we're not allowed to go. It's completely classical. And so we understand the whole global structure of the moduli space. And further, we understand all the kind of infinite distance limits or weak coupling limits that can exist in that moduli space. And they are classified beautifully using the mathematics of mixed Hodge structures or limiting Hodge structures. So this is a kind of example schematic diagram of a moduli space. You have all these kind of loci, and each one of them is infinite distance. And then they may also intersect, leading to all kinds of infinite distance loci or all kinds of weak coupling limits. So that's the setting. So let me give a little bit more details about it. So here's an example. Can you see my pointer? Yeah, a little bit. Here's an example of a moduli space for a one-parameter Calabi-Yau. So this one has 2 types of infinite distance limits. The point is that around any of these infinite distance limits, there is a kind of monotomy that you can do. You can go around them. And associated with such a limit, there is a monotomy matrix, which determines the local geometry on the moduli space. So let's see how that goes. The moduli space is Kähler, so the metric is determined in terms of a Kähler potential. And this Kähler potential is given in terms of the period vector, pi. And the period, here there's a symplectic inner product you have to take with the period vectors. And the monotomy is like this. If you go around one of these paths, gamma, around the infinite distance locus, then the period vector transforms by 2 pi I, and then that's equivalent to acting on it with some integer matrix T, and that T is the monotomy matrix. And that's true for any infinite distance or any weak coupling limit in the moduli space. It's usually better to work with the log of T rather than T. So you write T as e to the n, and then you use this matrix n which specifies the monotomy. And then the geometry of the moduli space is given by this formula, just the Nilbitten orbit theorem. And it says that near any one of these loci, the period vector takes this form here, this exponential form, log z, here. And the important thing is that all the other contributions to it are holomorphic. So it's just an expansion in positive powers of z. And you see that as z goes to 0, as you approach the infinite distance locus, obviously the log z terms dominate over these terms. And these are, in fact, exponentially suppressed relative to these. And so we should really think of these as kind of instanton corrections to the classical result. That's one way to think about them. So this is the Nilbitten orbit theorem. And perhaps the one thing we should take away from this for this talk is that the only singularities that you have are at z equals 0. You can see that this is completely smooth. So there's some log z divergences as z goes to 0, but there's no divergences here as z goes to 0, and there's no divergences anywhere else. So the important thing is that within the nilpotent orbit, the only singularities in the moduli space is the infinite distance point. That's what we will use in this talk. And whether a limit is infinite distance or not is related to this power of n, which doesn't annihilate this a0. So that's the first constant vector here in this expansion. And if the n to the dth power doesn't annihilate n0, then you can associate an integer d to that infinite distance. And d in Calabi-Yau threefolds, d can be 1, 2, or 3, and then 1, 2, or 3 is infinite distance. If d is 0, it's a finite distance singularity. So that's basically the moduli space and monotomy in one slide. If there's any questions, you feel free to ask. So what about the BPS states? What about the charge states? So that's the geometry of the moduli space. Now what about the charge states that are supposed to be part of these towers? Well, these are VAP-D3 branes, so their mass goes like, m strings, since that's the only mass scale in string theory. They're D branes, so it goes like 1 over G string, and then times the volume of the 3 cycle that they wrap. If you factor out the volume of the whole Calabi-Yau, then you can take this whole combination, write it as m Planck. And therefore, the mass in Planck units is given by this function z of q, their charge, and this function is called the central charge, and it's just given in terms of the period vector like so. So that's the nice thing. And now basically the idea of this talk, of this work, is to use the Nilbitten orbit theorem inside the expression for the central charge. And that gives us a completely general expression for BPS states at any infinite distance limit or any weak coupling limit. And then we can use that to study the properties of the BPS states. So that's what we're going to do. And what is it that we want to study? In this talk, we're going to focus about something in particular. We're going to talk about the stability of BPS states. So BPS states, as you move around the moduli space, can decay or combine. The spectrum of BPS states can change as you move around the moduli space. And this change in the spectrum of states occurs along codimension 1 loci in moduli space called walls of marginal stability, where essentially that's the only locus in loci moduli space where such a decay, a state can decay to 2 other states allowed by charge and mass conservation. So if you have some BPS state A, it may split into 2 BPS states B and C, it may decay into them. Obviously, the charges must be equal. Since the central charge is linear in the charge, then you have this equality here in the central charge. And then the central charge is related to the mass of the BPS state, that's the modulus of it, times some phase. And the wall of marginal stability is defined as the phase of the 2 constituents being equal. In that case, you have the phases of all these z's align, and so you have a relation with the masses like this, and that means that a decay is allowed by energy conservation, and it's only allowed on that locus. So another thing we can understand is that we can write this locus of the alignment of the phases as this equation here in terms of the real and imaginary parts of z. And this defines for you the wall of marginal stability up to one more condition, which you need to impose, which essentially splits the difference between, along this curve, there is a wall of marginal stability, and then there will be some point where it flips to an anti-wall of anti-marginal stability, where the phases exactly misalign. This equation doesn't differentiate between the two, but roughly speaking, this gives you the curve of marginal stability. So we will use that later on. And then, once you cross this wall, a BPS state may disappear from the spectrum, and the change in the number of BPS states is given by the Conservis-Solbermann formula. But there's a kind of simpler, primitive version of it which captures the physics that we need to know. If you have some state A that crosses a wall of marginal stability to a decay of state B and C, the change in the number of BPS states of charge A is given by this formula here. So we see that it's proportional to the inner product symplectic inner product of B and C. So that means that a state cannot decay. It must decay to states that are not mutually local with it. You cannot have a BPS state decay into states that are mutually local with it. So there will be no change in QA. Times the index, which is the number of BPS states of the constituents QB and QC. So that's the other thing. If you want a BPS state to decay, it must be that the constituents it decays to must be in the spectrum. So the change in the number of BPS states of charge QA is proportional to the number of states of the constituents that it's supposed to decay to. So that's the things we need to take away. OK, so that's the introduction to the setting. Are there any questions about this? These are just hypers. These are just the VAP-D3 brains. Yeah, so this index takes care of that usually. Yeah, so all the vectors drop out of this index. That's why people use it. It just counts the hypers. Any more questions? OK, so now I can go ahead and state the result actually in just 2 slides. And then I will talk about the implications of the result and about the proof of it. So the result is the following. Remember I said about any weak coupling limit, you have this monotomy matrix N. It turns out that this N has a certain, imposes a certain filtration on the space of BPS states. So that means that if you take the set of BPS states labeled by their charge, some vector space, that vector space splits into certain subsets. In the case of Calabi-Yau threefold, maximally 6 different subsets. W0, well, W-1 is an empty set, and then W0 up to W6. And the sets are defined by the images of the kernels of this matrix N that acts on the charges of the BPS states. And this splitting into different sectors of the BPS states is called, it's a filtration. What does that mean? It means that basically you have some subset of the BPS states, you call this W0. Then there's another subset, which you call W1, and W1 includes all the states in W0 plus some more BPS states, and so on and so on. Each W is some subset of the space that includes all the previous Ws plus some additional BPS states. So you form something like this, and the highest W includes all the BPS states, includes the full space. And this is called a monotomy weight filtration. It always exists around any weak coupling limit. So in any weak coupling, the BPS stays split into this filtration. And N is a matrix which moves you between one sector and a lower W. Okay? So the weight of a state is given by what is the lowest W that it appears at. So, for example, this red subset of states has a weight 4, you might say. It appears there. And that's one way to think about it. Are there any questions about this monotomy weight filtration? Okay, so this is a mathematical property that exists associated to a monotomy matrix. And the point of this talk and my work is to say that there is some physical meaning to this filtration. There is a physical meaning to this filtration. And the physical meaning is the following. Within any Nilbitten orbit approximation of the moduli space, so that means in any weak coupling limit, by weak coupling we mean that the instanton expansion is under control. Okay, so that means that you can, whenever you can write the period vector in this way, the claim is that a BPS state can only decay to constituents which do not have a higher weight. So that means that BPS state decays as you cross walls of margin stability anywhere within the Nilbitten orbit, can only go down in weight. So you cannot have, let's say, a red state decay into a purple or a blue state, only this way. So this filtration has a physical meaning, that's my claim. The physical meaning is a kind of stability filtration. It means that decays only go one way along this filtration. That's the result of the talk. Are there any questions about this result? So what I will do is talk about what does this imply, what are some interesting implications of this, how to interpret it, and then I will prove it. Okay. Yes. If you give me the monotomy matrix, I can tell you where that what the weight of the BPS state is. Well, no, you split your, these W's are defined by the N, and then you just look and where it sits, if it's in the image and kernel appropriately of N and N squared and so on. So it's completely determined. Sometimes it's hard. They can be huge. Of course, the vector space can be huge, like hundreds, but it can always be done. So let's give a very simple example of what this means. Okay, so the simplest example is so-called d equals 1 infinite distance loci, and those are just like kind of field theory loci in the sense that only two W's are populated, if you like. So there's only two types of weights, and this is what we would usually call electric and ionic states. So remember, it's a filtration. That means one has to include the other. So you have electric states. Those are the lower weight states. The higher weight states are dions. Dions include electric states, but they also include magnetic charges. So how do the masses of these states go like? Well, the mass of the electric state goes like g times the electric charge, and then mass of the dion goes like g times the electric charge and plus 1 over g times its magnetic charge. And then what does it mean that the state cannot decay to higher weight? It means that you cannot have a decay where an electric state decays to some dions. Yeah, so this formula is a little bit, these are not really vectors. There is an absolute value here, but these can cancel against each other. The electric and magnetic contribution can cancel against each other. That's an important thing. Yeah. Yeah, this is complex. Yeah, sorry. This is a schematic. This is a complex, this is central charge, essentially. So, and then you have to take the model. This is schematically what it looks like. So the statement is that electric state cannot decay to dionic states in any nilpotent orbit. That's what it means in this particular simple limit, but of course it's a completely general statement. So at first glance, you might think this is an obvious statement because electric states are light, and dionic states are heavy, magnetic states are heavy, but of course that's not necessarily true because I didn't say what the electric charge is. The claim is that this is true even if the electric charge is huge. So the electric state is some black hole the mass of our galaxy, an electric charge BPS black hole the mass of our galaxy, and the dion can just be a Planck scale particle. Claim is you still cannot decay to a dion, even if it's a huge black hole. No electric state can decay to any dionic state. That's the claim of the result. And in that sense, it's surprising because this decay is allowed by mass and charge conservation. It's allowed by walls of marginal stability. Electric states do cross walls of marginal stability to decay to two dions. That does happen. But the decay does not happen because of the population of BPS states, because one of the dionic states, I claim, will always be absent from the spectrum. So it's not a mass or charge conservation statement. It's a statement about the spectrum of BPS states in the theory. That's the claim. Are there any questions about this? OK, so what does this? Let me say three things that I think this might teach us about these infinite distance limits. So one thing is to do with dualities. So we sometimes can think of these towers of states as providing new fundamental degrees of freedom, but which we rewrite our theory, and they give us a dual description of the theory. So we might think that we're in some point, then we go to some infinite distance limit, we get new light degrees of freedom, we call those our fundamental degrees of freedom, so we change what we call constituent and what is fundamental, and then we use the new fundamental degrees of freedom to write a dual description of the theory. That's what we usually think about in terms of dualities and light towers of states. Now, my point is that this is somehow giving us a new understanding of dualities in the following sense. Approaching such limits, there is a new notion of fundamentality. That's what I claim. In fact, I believe infinite distance limits are precisely dual to a notion of fundamentality of, in this case, BPS states. So what I mean by fundamental is the following. A state which can decay to some other state is less fundamental than it. Okay, so if something cannot decay to another state, it means it's more fundamental than the state it can decay to. That's just a familiar notion of fundamentality. But the important thing is that this notion of fundamentality is not related to the lightness of the states in any particular reason. So as I said, even if you have a supermassive black hole, the size of our galaxy, an electrically charged one, I claim it is more fundamental than a dion of charge of mass Planck m. It can never decay to it. It is more fundamental than it. So this is a slightly different notion of fundamentality that you might guess. It's not just that they're light, but there is a more refined notion of fundamentality. And that's what the mathematics also tells us, because the monotomy weight filtration doesn't mean that one of the charges of lower weight is smaller or bigger than charges of bigger weight, because they can always be scaled up and down. It's invariant under rescaling. So it's not a statement about mass. It's a statement about the kind of splitting of type. So if you want to relate fundamentality to lightness, we usually say light states are fundamental. then the claim is that that is still true, but fundamentality of states is determined by the mass at g equals 0, at the infinite distance point. Because even if you start with an electric black hole at finite g, which is the mass of our galaxy, and a dion that's at the Planck mass, if you go all the way to g equals 0, eventually that dion will become heavier than the black hole. And so at g equals 0, the black hole would be lighter than the dion, and you would say it makes sense, it's more fundamental. Of course, at finite g, this doesn't make sense in terms of the masses. So the claim is that fundamentality of state is determined by the mass at the infinite distance point. And this is similar to this idea of the moduli space holography, that somehow the moduli space, and now also, I believe, the spectrum of BPS states, is determined by the infinite distance point. That's the claim. Okay. Another thing is related to this idea of emergence, which is that the infinite distance loci are, they arise from integrating out the tower of light BPS states. So in that sense, there are dual descriptions to the same physics, much like, for example, the conifold, where you have a singularity in the moduli space that comes from integrating out a D3 brane. There are dual descriptions of the same physics. You can either have the singularity or the D3 brane, but if you integrated the D3 brane into the theory, you don't have the singularity anymore. They're capturing the same thing. The claim is, of this proposal is that this is also true of the infinite distance singularities. They come from integrating out, not one, but an infinite tower of D3 states. And if that is so, then you would expect a correspondence between BPS states and the moduli space, a one-to-one correspondence. And the claim is that this is certainly part of it, if not all of it, that is infinite distance loci in moduli space are the same as a filtration of BPS stability. It's some notion of fundamentality in the BPS states. And the precise statement, the precise map is related from the Nilbitten orbit theorem. So in the Nilbitten orbit theorem, the moduli space is given by the monotomy matrix. And the monotomy matrix also gives you a filtration on the space of BPS states. That's the precise, it gives you two things, and the claim is that those two things are capturing the same thing. And the final thing is that it does shed some light on the question of proving that this infinite tower of BPS states is populated in the spectrum, because if you have a BPS electrically charged black hole in the theory, that is non-trivial if there exists or not, because the attractive flow diverges for electrically charged black holes. If the theory includes electrically charged BPS black holes, then the tower of states at infinity must be populated, and it's populated precisely by the microstates of the black holes. Because remember what I said, even if you start with a massive black hole, electric charged black hole, it cannot decay at any point within the Nilbitten orbit. That means if you take g to 0, those microstates of the black hole cannot decay at all the way to g goes to 0. So that means if you think about some finite value of g, give it a big integer charge, so you have a black hole, and then you send g to 0, so this black hole goes through the Planck scale, becomes sub-Planckian. Throughout this whole transition, it cannot lose any states. It cannot lose any degrees of freedom. That's what I argued for, and therefore the light tower of states, when they become light at g goes to 0, are precisely the black hole microstates. That's what this proves. Okay, so let me just give the proof of it. It's rather quick. I have 40 or 30 minutes. I don't. So I have lots of time. Okay, so there's kind of two arguments for proving what I just told you about this stability filtration. One way to think about it, and they are basically dual to each other, or they're capturing the same physics. One argument is by thinking about black holes. So there is a proposal that in n equals to supergravity, you expect a correspondence between BPS states and BPS black holes. And this correspondence goes roughly like this. If an attractor flow exists for some black hole of charge q times m, where m is some large integer, so it's a large charge, then there is a BPS state of charge q in the spectrum. That's what the proposal, and I will give evidence for this. I believe this is correct. And so using this correspondence, what does this imply for these decays that I'm talking about? Well, if you have a decay of a Waller margin stability of some electric state going to two dionic states, what this means in the language of black holes is the following. You have two center black hole, such that two black holes, dionic black holes, such that the total charge is electric, and you have an attractive flow which splits at some point onto those two black holes. So that's a split attractive flow. That's the black hole description of the BPS stability that I talked about, a decay of BPS states. And what you can show is the following. If you change variables from log z over 2 pi to t, which means that the physical part of the moduli space, the Nilbitten orbit, is the imaginary part of t much bigger than 1. That's in this change of variable. Then you can show that there is a relation between the attractive values of the moduli at the black holes and the point of Waller marginal stability, which is this, for this solution to in any such solution, and this can never be satisfied for positive values of imaginary part of T. In other words, if the attractive values are positive, so they're good attractors, and the Walder margin stability is in a good point of moduli space, this you see is always smaller than 1, and that proves that this cannot exist. So the claim is that such attractive flows do not exist within the nilpotent orbit approximation. So the fact that such attractive flows cannot exist is already telling us that somehow this cannot happen. BPS states you cannot have BPS states doing this. And what you can further show is that, in fact, no center, any number of centered attractive flows cannot exist. So you can take any number of dionic black holes, and if there's total sum charges electric, you will never have such an attractive flow. You can prove that, at least in d equals 1 infinite distances. And this gives us hints that such decays cannot exist because one of the states in the spectrum is not present. We have a bad attractive flow for one of the black holes. But you can even prove it. This will give you evidence, but you can even prove it more generally by understanding the following, by understanding better this relation between black holes and BPS states by thinking about when does the BPS state have a 0 mass. So if you have a certain charged BPS state, you can ask when does the central charge vanish on the moduli space. And what you can show in these infinite distance loci is that the point where it vanishes is exactly minus the attractor locus of the associated black hole. Okay, it's exactly the negative of it. So having a negative attractor locus, which you had to have for one of these black holes, is the same as saying that one of these dionic constituents has a 0 point, its mass is 0, somewhere that is at positive values of T. That means at a good point in the moduli space, within the nilpotent orbit. Okay, so what you can understand is that if you have a decay of an electrostate to 2 dions, one of the dions must have 0 mass within the nilpotent orbit, so in the good region of moduli space. But, so this is the picture. If you had some decay of some state A going to B plus C, whilst crossing a Walder margin stability within the nilpotent orbit approximation, one of these states, decay states, must have a 0 somewhere along that Walder margin stability. That's what you can show. And I'll give very general arguments why that must always be the case. It's very simple, actually. But we know that no BPS states become massless within the nilpotent orbit. That is precisely what the nilpotent orbit tells us. The only singularity in the nilpotent orbit approximation in the moduli space is at infinity. And if you had a populated BPS state becoming massless, it would induce a singularity in the moduli space, just like in the conifold. Therefore, any state which has a 0 within the nilpotent orbit must be absent from the spectrum. And so the decay is not possible because one of the states must be absent from the spectrum. So that's the understanding of the result. If you have a decay which violates the stability, one of the constituents must have a 0. If it has a 0, since there's no singularity in the modular space, it cannot be in the spectrum. And that proves why this is not possible. Now, you can understand this a little bit more detail by looking at d equals 1 loci. The point is that in d equals 1 loci, the Walder margin stability is just straight lines. So straight lines go all the way to infinity. That's an important thing. And anywhere along that line, you have an equality in the masses. And so now we see why there must be a 0 completely generally. The point is this. Remember what I said, that the weight determines the mass of the state at infinity. Okay? Imagine you're at finite g, you have some decay, which violates the weight filtration. Then you go along this Walder margin stability to infinity. Since the masses are equal anywhere along that wall, since one of the states has a higher weight, that means its mass must get higher than the original state at some point along that wall as you go to infinity. So, for example, here you can have an electric black hole, the mass of our galaxy, decaying to a light dion if you want. But if you go all the way to infinity, eventually that dion will become heavier than the black hole. When the masses become equal, let's say when the mass of MC becomes equal to the mass of MA, since anywhere along that wall you have an equality of the masses, that means that the mass of MB must be 0. So when you violate this filtration, and eventually somewhere as you go to infinity, one of the constituents become equal mass to the original state which did decay to it, the other constituent has a 0 mass, because you have this equality all along it. And that is precisely this 0 point that I tell you that is always there. And, of course, if it has a 0 point, it cannot be in the spectrum. In fact, the 0 point is precisely the point which separates this wall marginal stability from what's called an anti-Walder marginal stability, where the phases misalign. Are there any questions about this? Yes? You could say that the wall terminates on this point. Or you could say that it turns into a wall of anti-marginal stability. Yeah. No, so there are two types of walls. D equals 1 loci, they're just circles and straight lines. In general, there can be all kinds of things, walls. They can terminate also on the moduli space. But the point is that if you have a good decay that satisfies the weight filtration, then this is not true, that you always have the mass of one of the constituents becoming equal to the mass of the original state somewhere along the wall. Because let's say you had a dionic object decaying to electric states, or a magnetic object decaying to electric states, then you can go to infinity, and the original state could always stay more massive than the constituents. But that cannot happen if it was originally an electric state. Even if you started with a very massive one at finite g, by the time you send g to 0, that's always going to become at some point lighter than constituents. And then you will get a 0. So that's the general understanding of it. Now, this also shows why you can't try to avoid this conclusion by doing the following trick. You could say, OK, let me do the decay here, and then the B has a 0 here, and so it cannot be in the spectrum, but maybe it decayed away from the spectrum by crossing some wall of marginal stability between this decay point and its 0. So that's a possible way to get out of this argument. Okay, so it was here, so it decayed, but then it crossed another wall, it disappeared from the spectrum, and so it's not in the spectrum when you have a 0. But the point is the following. The point MB goes to MB equals 0, the 0 point, must sit on the wall marginal stability of any decays of the state B. Because the wall marginal stability is defined by this equation, and MB equals 0 is the real part of Z equals the imaginary part of Z equals 0. So it always satisfies the equation for the wall of marginal stability. And therefore, any wall of marginal stability for the constituent B, which has a 0, goes through that, must go through that point. And so it cannot have decayed before it reached that point. So this cannot happen. This proves that you cannot get away, try to get around this by this. Now, it could be, since this state is a dion, it could have decayed to 2 dions. So if it decays to dions and not something that has different weights, it's not a straight line but a circle. But the argument is still the same. If you had hit some other wall of marginal stability, that wall has to go through this 0 point because it's a solution to the equation. And so if B disappeared from the spectrum by decaying into D and E, let's say, at this point, MB equals 0, and so MD and ME are also 0, because they have a mass equal here. And so you would still have got a singularity. It means you cannot get away from this 0. If you decay to something else, one of the things you would decay to would have also a 0. And that's precisely the statement, due to the statement that I said that if you have multi-split attractor flows, if you try to keep splitting the attractor flows, you can never turn a bad attractor flow into a good one. That's the same thing here. You can never get rid of a 0. A 0 will always stay throughout any decays. So that's all these pictures are true for D equals 1. They're just straight lines or circles. For general D, the walls of marginal stability can be more complicated. But what you can prove is that for any D, any infinite distance locus, walls of marginal stability go to straight lines for sufficiently large imaginary part of T. So if you go sufficiently close to the weak coupling limit of infinite distance, all walls of marginal stability which violate the filtration are always straight lines. And so all the arguments I just gave are completely general for sufficiently large distances, sufficiently weak coupling, any infinite distance. In fact, they don't have to be straight lines for the argument to work. They just need to reach infinity. If they reach the infinite distance locus, you always give this argument that one of the states becomes heavier, then you always get a 0. So this is completely general. So that's the proof of the statement. So to summarize, we see that any decay which violates the filtration must lead to a moduli space singularity at finite distance. Since there are no such singularities, that is precisely the content of a Nilbitten orbit theorem, that there are no such singularities, that is equivalent to enforcing the stability filtration, saying such decays cannot occur. The weight filtration is not a mass filtration. That's the important thing. It's not a mass filtration. It's a mass at infinity filtration. Okay? So a very massive electric charged black hole could be heavier than a dion, but it's still more fundamental. It cannot decay to it. One should be a bit more careful. The monotomy filtration is actually not quite refined or precise enough for the things that I said. One should really use a Deligne splitting because you need to have a polarized inner product. But this is details in some sense. So to summarize, BPS states satisfy a stability filtration, which is determined by the monotomy about infinite distance or 0 coupling. This is consistent with the idea of emergence. It's a qualitative connection between moduli space geometry and a BPS spectrum. infinite distance limits are the same as an ordering or filtration of BPS stability, some notion of fundamentality of BPS states. So some types of states can decay to others, but not the other way around. The stability of BPS has a microscopic description in terms of strings stretching between the branes and becoming tachyonic or not, so it would be interesting to try and understand what does having this kind of ordering or filtration on the spectrum of BPS states mean, can we understand it from a microscopic perspective? And as I said, this could lead to proof of the distance conjecture in the sense of also proving that all the states are populated in the tower if you can show that electric black holes exist in the theory. So another way to think about it is the weak gravity conjecture is proven in this setting in the sense that all the BPS states are populated, infinite tower BPS is populated, if electric black holes exist in the theory. That's the same thing. And then the states are precisely the black hole microstates that become light as G goes to 0. That's it. Thank you.
Thanks a lot. Thanks for staying through the time that we have. Suppose you don't do supergravity, but just for the inequality field theory, do you also expect a filtration in the set of BPS states?
Yes. I think the D equals 1, the electric and magnetic thing are like geometric engineering limits within the supergravity, so you can kind of understand it as a field theory statement.
Do you expect that there is a way to derive this filtration from, for example, BPS quiver of the theory?
Maybe, I don't know. Yeah, that is with microscopic understanding. I don't. The question was, let's say we look at particular infinite distance limits that are essentially like geometric engineering limits, and then you can understand them as field theory statements. Should this be true then? And I think the argument is still yes, because it's still true that a massless state gives you a singularity in a moduli space, and there are no, and therefore it would occur there. And then the question was, can you derive this from the quiver of the states of the theory? Some kind of open string picture? I don't know, but yeah. Possibly, it would be nice to understand this thing. Yeah.
You don't need a polar picture. This is basically the Witten effect, right?
I don't know if the Witten effect is like when you do go around with the axion, you pick up a magnetic charge. That's the monotomy. No, it's not really. It's not quite the same thing, I think. So it's true that you can understand. Let's say for the conifold, you can understand the monotomy is the Witten effect. So when you go around, the monotomy action on the charge can be understood as a statement that a state that you move around the charge picks up that charge as you go around it. This is not true at infinite distance. In fact, at infinite distance, the monotomy and these kind of lines that go to infinity, the relation between charges that are related by a monotomy, like in the conifold when you go around it, their wall of stability are straight vertical lines. In fact, so when you do, if you go to far enough distance, and then you will never hit that wall of margin stability. So they cannot be understood as a decay. So the conifold, I mean, actually, Mike wrote nice papers about this. The Witten effect can be understood microscopically as the decay of the state, and then it binds with the state that becomes massless, and then you get a new state, which. Oh, okay. Yeah.
Limit is the strong coupling point of Simon Witten. I'm talking about the weak coupling point. The weak coupling point is at infinity. That's the point where you have a tower of these monopoles and so on. And this Witten effect is just tells you why you have a tower, which is what you're saying too. Which is exactly what you're saying.
Yeah, it's not. I don't think. So the tower that you get by acting with a monotomy acting on the state.
Yeah, same
yeah.
Monotomy, because for you the monotomy n is in the mirror picture, for example, is that you're taking electric to magnetic, like D4 to D2 mixes with D2 and D0 and so on.
Yeah, but the tower of states that are stable are the electric states, and the monotomy acts trivially on them. If you act with the monotomy matrix on the electric states.
Different numbers. Suppose you take mirror picture of what you're saying, and suppose you take the large complex structure mirroring the volume being leaked, for example.
Yeah.
Then suppose you have a D4 brain.
Yeah.
And D4 brain, as you go around, the thing picks up a D2 brain.
Exactly. Yeah.
That's Witten effect.
That's the Witten effect. That's I agree with that, but that's not.
That's not what you have the n in that case, not mixed.
It's the same n, yeah, but that's not the argument that I mean. How is that related to what I was saying precisely?
Your population of n going down in the tower, isn't that the same as populating D4 with D2s? Adding D2s to it?
In this language, the statement is that D4, D2 bound states, so you cannot have a D2 state decaying to a D4 or D4, D2 bound state.
I'm not talking about the decay. I'm just talking about the population were showing how you populate it.
No, you don't populate it like that by these ends. This is not I've not shown that they are populated. That's the only way to argue that they're populated is by black holes. If black holes exist, then you can argue they're populated. But I've not said anything about.
You start with one, you said how you get the rest, right? Doesn't have to be.
Yeah.
Black hole argument for that. I'm talking about that part of your argument.
Yeah. So this we made an argument similar to that. That you start with one and you populate the monotomy orbit. Yeah. So this we made in an old paper from 2018. No, but this cannot be general because generally the orbit that you generate will act trivially on the light states. I say d equals 1 loci. If you act on the electric state, you will not get anything. In large volume limit, you can act on d2 states and then you get d2, d0 bound states. And this way you can populate many. But if you act on d equals 1, like if you act in electric states, you cannot populate a tower using this. So in certain cases, you can make an argument using that. And we did that in 2018. But still, you have to show that at least one in this orbit is populated.
So you're saying in some cases, the ones that you're having sometimes mix up electric with electric, not with magnetic. The end that you were doing.
No, they never mix electron with electric. That's the point. So sometimes they can. A large volume they can do. Because then you have d0, d2 are both electric. And then you can pick up d0 charge. So that way you can generate a tower with this Witten effect. And we pointed that out in 2018. But generally you cannot, because if you take an electric state and you try to generate an electric tower, the monotomy will not do anything to the electric state. Yeah, okay. Yeah, I'm not. I think in all the cases I know, if central charge vanishes, you get a singularity if it's populated. But maybe there's a way to try and avoid it. I would have to think about that. Yeah. But I think for decay to occur, you need the index to be non-zero. So in the wall minus stability, the change is proportional to the index. If you want the index to be non-zero for that state, then it must induce a singularity. So I think, yeah. So I don't think that's a, yeah.
Is it possible to use this technique to really compute BPS indices, for example, with the mean of the large volume?
Yeah, not that I know of, unless one can. There is some complicated graph of these walls of marginal stability. So the only thing that this tells you, the only thing I use is which states are absent from the spectrum. I don't know how to calculate actually how many are present or the multiplicity or anything like that. So this I do not know how to do. So that's all I can do at the moment.
Any further questions? No? Okay, then let's thank Eran again.